Hello, everybody. Great to see you. Feel free to say hi in the chat. As always, if you're new here, please let us know where you're coming from. It's a busy time in my life. We have finals week this week at Carnegie Mellon. So there's been plenty to do with that and students finishing up projects. Looking forward to the summer. Should be a lot more planning time that I can devote to this and roll out our next set of classes. Can't wait for that. We also have our first round of projects for our Philomath members. And so we saw our presentations on those for our learners who wanted to present their work. That was a few days ago, and the work there was fantastic. So everybody's effort on the projects was really good. I think everybody who completed a presentation really truly went above and beyond. And I felt like I learned something in everybody's presentation. So that was really good. If you're interested in doing a project, keep an eye out for messaging about two things. Our next cohort of projects that accompany part one of the course. So if you're still kind of keeping up, but you want to do a part one project, we're going to have a way of doing that. And then we're also going to have some projects for part two. So if you want to practice doing object-oriented programming, parallel programming, all that good stuff, we're going to have an opportunity for you to do a project around it too. So make sure you're on our mailing list because we'll have messaging around that going out this week. The other thing I was curious about too, while I have you here, just to ask the chat, is to ask an informal question of you, which is, would you be interested potentially if we had a project that was around using AI in a productive manner to scale up what you're able to do with building a programming project? So for example, like how to vibe code effectively with science in a way that might get you to a result and allow you to analyze things just as much, but also as we're taking the training wheels off and we appreciate how to program on our own, how is it that we effectively use the tools that are out there to build something even faster and bigger? I'll probably put that in a poll. We're going to ask folks about that and see what they think. But if you have any particular thoughts about it, just let me know in the chat. A lot of times that's what I allow my students to do. In my other courses at CMU, we kind of let them use AI as much as they like, as long as they're able to justify what they do and build something cool and understand and can communicate all that. All right. Look out for an email though, and as I said, if you're not on our mailing list, not in our Discord, hop on those. And it's good to see some thoughts on this. Seems reasonable. That I'm glad to see that folks might want that, but we'll put productive AI, Remy. I like that. So the idea is not to just blindly vibe code something without any kind of knowledge of where you're going. And in my case, even with building, some of the stuff that we do here and making sure that it's educationally effective, it's just so helpful. But I feel like I've acquired a lot of skill sets around this that a lot of times when I see students working with it, I don't think they actually know the best practices for how to use these tools to effectively learn and build something. So let's see. I'll send around a poll. Last time we talked about parallel programming though, and we did a really simple demo. And that demo was taking the elements of a list and summing them. So we wrote this code. We just have everything in main. And I want you to remember kind of how everything works. We chunk our data in some way. We make these worker processes. We make sure to start them. And then in a separate loop, we join them, which means wait until everybody has finished. And then all of these processes have worked with a queue. and they've placed their results into a queue, and then we go in and we grab them and process them in some way. So that queue is first in, first out. The first worker to finish is the first worker to be able to put its answer into the queue. And what we found was, well, Python has a lot of overhead, right? So we had hoped that this simple function that we wrote might produce a speedup when we time it against just summing the elements of a list serially, meaning range over the list and add up all the values into a sum value. If we instead split this over a bunch of cores, we might think that we would get a speedup, but we actually don't. And so I would hit the limits of the amount of memory that my computer has to make a list big enough to finally see any kind of improvement with parallel. So we were getting better. Our performance was kind of improving compared to the serial approach, but we never actually saw a parallel approach being faster. Tonight, what we're going to see is that it is not the case that parallel programming is pointless. Even though Python has overhead associated with parallel programming, meaning it will be a little bit slower to set up everything behind the scenes to make parallel programming work. Even though that's the case, we're going to start seeing examples where parallel programming does work, is very much worth doing, and shows us a tangible improvement in terms of runtime over how I've hopefully brainwashed you up till this point in the course to think about programming, which is one step at a time, everything serial. It will be worth it if we see two things. So two things have to be true for it to be worth it for us to make this transition. Number one, it probably should be easy to divide the tasks over workers. So when we create these processes, it should be clear how that process is actually going to be achieved. And two, and this is going to be really important, it should be also the case simultaneously that every worker also has a lot to do. And that's kind of the problem with what we're seeing for this summing the elements of a list in parallel, which is that I'm not doing anything complicated enough to really possibly see a benefit that would outweigh the high overhead that Python is charging me for setting up parallel programming. And so maybe if I give all these workers something harder to do than just sum the elements in a list, then I'm going to see the benefit of splitting that task. So again, can we easily split the task? In this case, for summing the elements of a list, we could easily split it over a bunch of workers. If I have two workers, you take the first half, I take the second. But it's not really the case that each worker is doing anything pretty sophisticated or hard or computationally intensive. And so as a result, yeah, I created the overhead, but I didn't get the payout that I should see from splitting the task. So we will see a natural example today of an example of something that has both of these things built into it. Our first example that we're going to see is a Monte Carlo simulation where we have lots of trials. So the example that I'm going to use is a casino game, craps, which we have already actually implemented serially. And I want to extend it to a parallel simulation and then compare the runtimes. So to say, how much faster is the parallel approach than the serial approach? That meets both metrics, I hope. We will see. So is it the case that this is easy to divide over multiple workers? Yes. Is it the case that each worker is doing something reasonably sophisticated? I think also yes, in that they're going to each be running like 1 million trials. And so I want you to conceptualize this as working is to say, imagine that, we all go to a casino, me and everybody in the chat. And I'm going to sit in the middle of the casino and I'm not going to do anything. But everybody else is going to go around and purchase many outcomes, or contracts, I should say, on the outcomes of the games of craps. Now, the casino might call that gambling. If you followed me before, you're going to know I'm very careful to call anything gambling. So I prefer to say that we're going to have you purchase contracts on the outcome of the game of craps. But what you're going to do is you're going to play for the same amount each time. You're going to keep track of the amount won or lost over the number of trials. And if you all play 1,000 games, you come back to me and report back and say how much you either won or lost. If I have input from 1,000 people, I just take each of your contributions, average those, divide by 1,000 after I sum them up, and then that gives me a good sense of what the house edge should be. So if we do that for a lot of trials, on average, we're probably going to collectively lose. Each individual worker might have a chance of winning, but probably in total, everybody is going to lose on average. And the idea of splitting the work over a bunch of processes makes sense here. For that reason, a lot of times we'll say that Monte Carlo simulation, or certain types of it, are what are called embarrassingly parallel, meaning it is such a clear and obvious framework that's reusable for taking any Monte Carlo simulation that you're running over n trials and just splitting that in over a bunch of processes or workers, that it's embarrassing to say out loud because it's somewhat obvious. We also want to build a scientific example, though. We've already worked with craps. In our first example, I want to move through it reasonably quickly because it's an extension of what we've already done. What I really want to do is build a reaction diffusion simulation. And that is something that we have already seen at the level of cellular automata with Gray-Scott. So if you've done our practice exercises, we've already seen the concept of having particles move around in space, and you have multiple types of particles. And as they move, as they diffuse, they also are allowed to react in some way. And in the Gray-Scott simulation, we zoomed out and we said, I'm not going to track individual particles, but what I am going to do is grid off the space into a bunch of cells and then think about how the cells send their particles around to neighbors and how, based off of the concentrations that I'm storing at a certain point in time, how is it that that's going to be implemented with chemical reactions. And so that was a really nice idea. I would actually like to build a version of that where we track all of the literal individual particles around and try to show how, hopefully, when we turn this simulation into a parallel simulation, meaning we're going to divide those particles over a bunch of workers and each one is going to be responsible for a subset, hopefully that's going to allow us to produce a simulation that's faster if we run it in parallel. That's too much to do in one sitting. And so what we're going to do instead is I will start getting you in the mindset of doing this by building a single particle diffusion model. So we're going to build essentially just a random walk of one particle moving around, or one type of particle. We may have 1,000 particles, but all those particles are going to move around. They're going to move in random directions. And we're going to visualize it, but we're also going to compare how long does that take if I do it serially? How long does that take if I do it in parallel? And can we compare them? And so that seems like it follows the same two ideas. It's easy to split this task over a bunch of workers. You might imagine we're going to divide the space into equally sized pieces. And if a point is in that particular quadrant or whatever, it's going to get assigned to that worker. And then we're running this diffusion process, so presumably that's going to be complicated enough to hopefully see an improvement at the parallel level. But we're going to see that. We're going to start with our parallel crap simulator. And if you want to follow along, we have some starter code in the description of the video. So just check that out there. It's easy to get. I also sent it around to our mailing list. And we're going to start with parallel craps, as I said. So I'll get that ready to go here. And that sounds like a pretty good reason to join our mailing list if you're not on it already. As always, of course, like and subscribe, please, to keep us visible. And I think we're ready to start, so let's code. If you have any questions as we go, as always, feel free to let me know. All right. Now, to get started, you'll see that I have a folder called Parallel Craps, and I have 3 files associated with it. So I already have some starter code for us. The starter code is going to run a number of trials of the game Craps, and then it's going to time the 2 approaches that we come up with. So we're going to have a parallel approach, and we're going to time a serial approach, and then hopefully the parallel approach is going to be faster. So we're going to take the ratio of the run times, and if the parallel approach is faster, say 3 times faster, it's going to take 3 times longer for the total serial. And if that's the case, when I do this, I'll get, division equal to 3. We, of course, need to write each of the 2 functions that I care about. And we previously wrote a function to compute the Craps house edge. We weren't using parallel programming, but the idea of this is, here was really our first introduction to the concept of making sure we have nice, modular, top-down design code. We have a compute Craps house edge function, and we pass as much work as possible to one of our subroutines. In this particular case, I'd say I'm going to run this for a number of trials. I'm going to keep track of how much I've won. And each time I'm assuming that I'm wagering a single unit of currency. And if I win the game, I'm going to get that back plus an additional unit. So my win total will go up by 1. If I lose the game, it'll go down by 1. And then at the end, I just say how much have I won or lost. If I've won, this win total is going to be positive. If I've lost, it's negative. And we divide that by the number of trials. So straightforward function. At this point in the course, I think we're very comfortable with the notion here that we've passed all of the work to this play Craps once function that's going to return a Boolean value, and it will return true if we win and false if we lose. And then we saw, well, here's where the rules of Craps actually get implemented. And this is not something that we really even need to know in order to parallelize this algorithm, as we're going to see. But the idea is you roll 2 dice, and if the sum of those dice is a 7 or 11 on the first roll, you win, so you return true. If it's a 2, 3, or a 12, then you lose, and you return false. And then otherwise, in other words, we roll something else on the first roll. You continue rolling, so we have the dreaded while true, and we continue rolling by summing 2 dice. And if we ever have that it's the case that the current roll is equal to what we rolled the first time, so if first roll were 6, for example, now if I roll a 6, I win. And now, even though 7 was a lucky number on my first roll, it becomes a losing number on subsequent rolls. So if I ever roll a sum of 2 dice equal to 7, I'm going to return false because that's now a loser. That's my very rapid refresher of the rules of Craps from the perspective of the person rolling the dice or betting with that person. And then, of course, we have a sum dice function, and here's where we saw this idea that a lot of times simulation is a lot cleaner than doing a bunch of complicated math. So I can simulate the process of rolling 2 dice by rolling a single die twice, and then adding the result of that die roll into a total. So I wrote this as an arbitrary function that could take 100 dice as input, and that would return the sum over all of those dice of what's showing. Then finally we get to the bottom of our function hierarchy, so to speak, and we have our nice simple subroutine roll die that simulates the process of rolling a fair single 6-sided die, and it just returns a random integer here between 1 and 6. So that was in sum, that is our Craps simulator. And what I would like to do is write a parallel version of this. So I'm going to place all my code for that in parallel.py. And you see that I've got a couple things imported. I've got multiprocessing, which is going to handle all the parallel parts of our code. I've also imported play Craps once from serial, and you'll see why I've done that here shortly. Here is where I need to think about what is my highest level function going to do. Well, I'm computing the Craps house edge. I'm doing it in parallel. I need to know how many total trials I want to run in the same way that I did this for a number of trials in the serial case. I need to know how many workers I want to divide the task over. So if I know that this computer has 16 cores, for example, it would be a good idea to divide this into 16 pieces. That way each core could work on one. And otherwise, what we're going to see is, hopefully I can still use the functions that I have in the serial side of the code, but I want to apply the same paradigm that I used to think about how to take a task and split it up in parallel that I used when we summed all of the elements of a list. So our highest level function here, compute craps house edge parallel, needs to remember that there's an order in which it's nice to do things that I think we can apply in a lot of different contexts when we program in parallel. And the order would be, well, first off, we create a queue to store our results. Things get weird with functions returning values when we parallelize our code. And that's because it's hard to know at any point in time if we have lots of different pieces of our code running. It becomes challenging to track what it means for a function to return because a lot of things are going on at the same time. Instead, that's the nice aspect of using a queue, because the queue is just accessible to all of our worker processes. And as soon as one worker process finishes, the queue allows us to have a shared collective source of data. And when each one finishes, it just drops its own whatever it was going to return into the queue. So we saw that previously. The second thing we're going to do is initialize our worker processes. The third thing that we are going to do is start the processes, and which will put their return values into the queue. We're going to range over all the processes and join them. And all joining them together means, or joining them means, is wait until all are finished before continuing. And then the fifth thing that we do is grab all results from the queue and combine. So we just need to take that collection of steps then and apply this to the context of computing the craps house edge. And yet on a very high level, we're going to do the exact same thing that we did before. I'm going to have a win total that's equal to 0. So this is me sitting in the center of the casino and waiting on everybody to come and chat to me about how many trials you played and what your end result was after making, say, a unit wager on a collection of however many trials each. So I'm the global variable here, win total, that's going to store the total amount won or lost over all of the workers. So I'll specify win total stores this total amount won lost over all workers. And then at the very end of this process, I'll say, well, once I've got the win total from everyone, I'm going to return that win total divided by the number of trials that I run. And there's nothing parallel here. This is on a high level just what the function needs to do. Of course, I need to do the parallel parts of the code too. So the first thing that we said we do is to create a queue to store our results. Let's begin then with setting a result queue variable, which is a queue, equal to an empty queue that comes from our multiprocessing module. Once I have established that, I'm also going to create a collection of processes that are going to be my workers, and that's going to be empty as well. So I should say create our queue and an empty collection of processes. So I have no workers currently, and there's nothing in the queue. The next question I want to ask is, there's kind of a 1B, before I even initialize the workers, there's an important question, which is, how many trials should each of my worker processes take? Or, in other words, be given? That's a good question for the chat. And I think thinking about it in terms of real numbers probably helpful. If there's 100 people and we want to run, 100,000 trials, how many trials should each worker get? And how do we generalize that, more importantly? Teresa, thank you for your answer there. Welcome, of course. Feel free to let us know where you're coming from. But yeah, glad you're here. And an immediate correct answer. That's good. So if we have 100,000 total trials, we have 100 workers, I said, we're going to have 1,000 each. And Javier, thank you. What do I do to generalize this? In general, the number of trials each worker should get is just, the total number of trials that we want to run divided by the number of workers. That's fair. Let's allocate things in an equal fashion. So I'm going to declare that to be a variable called trials for one process equal to the number of trials divided by the number of processes. I want to make sure that I perform this as an integer division because it needs to be an integer. So I have the double division here to indicate that this needs to be an integer at the end of the day. There's just one issue with this, though. What is it? What are we missing? Alistair remembers. Great. Good. As we saw when we were summing the elements of a list, you could wind up with some extra things. So in particular, for example, we need to be careful. So if the number of trials is, 1,003, and the number of processors is equal to 10, well, trials 1 proc would be 1,003 integer divided by 10, which is 100. But if we give 10 workers 100 trials each, we're only going to have 1,000. So we're going to be 3 short. And so the final worker should get 3 extra trials. Otherwise, we haven't really made sure that we cover all of the trials that we have. Fortunately, this is going to be easy to handle. But it means that the first n-1, or the first num-procs minus 1 workers, are all going to get trials 1 proc trials for them to run. And let's go ahead and start those first num-procs minus 1 workers. So we're going to start the first num-procs minus 1 workers. So to do that, I could have a for loop. I don't really care about the index that we have, so I'm not going to name it anything, but I'm going to say let's range up to the number of procs minus 1. So that'll give me n-1 total visits through the for loop. And then I want to create a process. So I want to make my worker, and my worker needs to be called multiprocessing.process. And remember, this takes target equals something, and it's going to take args equal to bar. But bar is going to need to be a tuple. So target is the name of the function that I care about, and bar is going to represent the arguments or the parameters to that function. And the function, I've already got a function signature for it for us, is going to be called total win 1proc. So I'm going to go ahead and copy that into the target that we have. Let's make that a little wider. And then the arguments that I want to give it, well, let's look at what total win 1proc is doing. This is what I call a worker B here. One worker B is going to play it for its number of trials, and then it's going to place the amount that it wins or loses into the result queue. It's not actually going to return anything, because when we're working with these function calls in parallel programming of all of my worker processes, I don't have to think about returning anything. I just place the value into the queue. So I will write this function, but I just want to make sure that I give it trials 1proc and the result queue that I declared. So that's what we have here. Now that I've done this, I just need to start it. So I will append it to the list of processes. I want to keep track of these things because I'll eventually need to go through and join them all, which will make sure that we wait until they're all finished. But I'm now ready to start. So this just adds P, my current process, to a list, and start simply begins the work of this current worker. That was kind of step 2 and 3. So we've initialized the worker processes, and then we started the workers. So they're all going through this, and when I start them, each one will start its work. Meanwhile, the for loop will carry on. A new process gets created. It's added to our list of processes, and then its work begins. So even if I do this for 100 workers, the for loop will continue. Each of the workers will start their work, and the code is going to carry on. That means if I give the workers enough work, I could reach this point of the code, and this part of the code will continue executing while those workers are still going. So that's why we need to make sure that we also have a separate process to wait on all the workers to finish. Now, I have missed something, of course, which is that I need to start the final worker's job too. But I want to make sure that I'm clear that after I start everybody's jobs, I need to wait on everyone to finish before I can return anything. This would be a bad line to hit if we're not certain that all the workers have finished. So in the meantime, we want to start the last process. And remember that we could have additional trials. Presumably they're not going to be a lot. In this particular case, the final worker gets only 3 extra trials. But we need to write out, a precise number for how many extra trials does the final worker get. So in general here, in this particular case, the final worker gets 3 extra trials, but we're not working with specific values, right? We're working with these number of trials and number of processes input parameters. So if I were then to say extra trials is equal to something, and then I said trials final process is equal to the number of trials that one process normally gets plus the extra, what belongs as the value that extra trials get set to? I'm enjoying getting to say Captain Fuzzykins. That's a good one. Also, I think a first-time chatter, so great. Number of trials, not divided by number of processes, but percent. Remy also says we're taking a modulus, right? Yes. So we're dividing here. What we want to do is divide the number of total trials by the number of processes that we have, and then take the remainder. So any remainder that's left over, which for this example was equal to 3. So when we do 1003% 10, we would get 3. Any remainder that's left over gets assigned to the final process. So the final worker will get a little bit of extra work, but not a lot. And once it gets that extra work, we want to start its job. So I will declare one more process, p equal multiprocessing.process, and everything is going to be really the same. So the target is going to be total win 1 proc. The parameters to that function that I call are going to be, well, not trials 1 proc, but trials final process. So the number of trials for the final worker. And we're also going to say, you know, at the end of the day, put them in the queue. So at this point in time, we have now started all of the workers. And then we go to step 4, which is to range over all of the workers and join them. So to wait on all of the workers to finish, we have a separate loop that says for every process, every worker that I started, we want to call p.join. And remember, there are 2 ways of thinking of this. Okay. Way number 1 is every time through the loop, the current process will not allow the code to continue on, so continue executing, unless this process has finished, meaning the function is over. And secondly, the only way I can make it through everything in the loop is if they're all done. So the only way I will eventually get through calling p.join of every process is, you know, these 2 lines of code wait for every worker to finish, and that's a good thing. Of course, in this particular case, I would get a pretty major issue because I forgot to start the final process. So I need to append it to processes, and I need to start it. Okay. Then we look at our framework and we say we've ranged through all the processes and join them, meaning we wait to continue until all of them are finished. And then we need to go into the queue and grab all of the results. So the values in the queue correspond, in this particular case, to the total amount won or lost by each associated worker. So each worker reports back, and I have lost control over the order in which they're going to report back, meaning they may have placed their own individual values into the queue in an order that I don't have any control over, but that's okay. I don't really care. All I care about is making sure that everybody does report a value back. So step 5 is then to say, let's collect results from the queue. And to do that, I will say, I don't care about the index, but let's range over the number of processes. And as I do that, I want to call result queue.get. So this will grab whoever is at the front of the line. And then I want to take that value and I want to add that value into my win total. So this is where each worker is reporting back with the amount won or lost. And then at the end of that process, I return the win total divided by the number of trials. So our function now is complete. It follows the same general plot as what happened when we parallelized summing the elements of a list, but we're able to do something, I think, a little bit more sophisticated here. of course, we are missing something, right? And what we're missing is that I haven't written total win1 proc. So we've done a lot of the work. I think we've done the hard work because we've applied the steps that we know we need to apply. But I also need to simulate the work of our one worker bee. What does that one worker bee do? It plays craps for this number of trials. And then when it's finished, it places the result into the queue that it's given. This function is way easier than you might think. All it's going to do is keep track of a win total. And at the end, we're so used to writing return win total. But what differs here is we're not returning anything. We're instead placing that amount won or lost into the input queue. So we need to say result queue dot put win total. And that will place it into the queue. Of course, I don't want to just put a bunch of 0 values into the queue. That doesn't sound very good. What I want to do is range over the number of trials this worker gets and simulate the game each time, adding in the result to the win total. So I will say for, I don't care about the index, in range over the number of trials won proc, play the game. So did I win? In other words, when I call play craps once, did I win the game? And if I did, I want to add 1 to the win total. Otherwise, we lost, and I want to subtract 1 from the win total. And our function is done. So there's nothing parallel about this function. It is our worker bee function. It works serially in the same way that when we first thought about craps, this process worked. Notice how similar it is to the serial function, right? So this serial function did the averaging as we go. And in this particular case, the worker bee is just going to report the win total. But the structure of the function is the same. So even though we're in the parallel part of the code, total win1 proc, or the worker bee function, is not actually a parallel function. The only way in which it differs here is that it's placing that win total that's not divided by the number of trials into a queue at the end instead of returning it. If that's our function, then we're finished, because play craps once can simply be imported from serial.py. And play craps once is a function that the serial function has already written, and its subroutine of some dice is already written, and its roll die function is already written. We have done this when we worked with a serial implementation of computing the craps house edge before. So like lo and behold, right? Once we have a serial implementation, we've got a parallel implementation that's actually really fast to implement, and that ties in to these lower level subroutines that we already have. Hooray for parallel programming. Of course, there's one important thing. Well, there's two important things. Number one, I probably should check this function in main and make sure that everything's okay. And number two, I would hope that I would be able to have a parallel program that's faster than the serial program, because if I can't make a parallel algorithm that's faster than a serial algorithm, parallel programming is not going to go very far. But for now, I've got compute craps house edge parallel, number of trials and number of processes, and I could say, well, if just copy this out here, I'm going to take this stuff here and call that there. And say, edge is equal to this. So I've imported this from parallel, and number of trials is, let's clean this up a little bit here. And now we've used both of those, and I can just print that value. So remember, this is an average number. So over our 1,000 trials, what's the average amount won or lost? And if it's positive, If it's positive, then that's a value that we have 1. And if it's negative, it's going to be a loss. So in this case, I need to CD into SRC, which is parallel craps, where I've got my code. I want to run Python 3 of main.py. And our house edge on this trial is the edge. So if it's negative, that means that the house is winning. And I can run this a few times. This takes us back to when we first implemented craps and first introduced Monte Carlo simulation. Long ago and far away, we did this same type of thing. We saw sometimes it's negative and sometimes it's positive. So when it's negative, we've lost, and when it's positive, we've won. But what we know is if we increase this to 100,000 or a million or a larger number, some statistical laws are going to take over and prove to us that the house is very much always going to win, and the numbers are going to tighten around the house edge being about 1.4 cents on the dollar for every dollar that you wager over each trial. And so that's the average amount that you're going to lose. Of course, we need to make this value pretty big before we're going to start seeing these values really hone in. And, the true house edge is 1.4 something cents on the dollar per game. That's just making sure that our code seems to be in good working order, though. The second direction is the thing that we care a whole lot more about. And what we really care a lot more about is to say, let's go through and time the two approaches and then provide the speed up. So this is our old friend, the timing code that takes two algorithms, runs them, times them with a stopwatch, so to speak, and then keeps track of what's the difference between when we stopped the watch and started the watch, and print that out. So we have some nice, pretty printing here for both the parallel case and the serial case. And so it's just a matter of running it. Let's make sure that this doesn't take too long. I'm going to start this at 1,000 trials. You may remember, but my computer here has 10 processors available. So we're going to be dividing this into 10 workers, each getting 100 trials. So it's now time to run this. We're going to run the same thing, Python 3 main.py. What do you think we're going to get? Let me know. What does the chat think about what our speedup value is going to be? Remember, the speedup is the ratio of the runtimes of the two approaches. And if parallel is faster, this number is going to be smaller than this one. So a speedup of 100 would mean this total is 100 times bigger than this one. What do you think? What number do you think we're going to get? Any predictions? We think no speed up. You're such pessimists. Let's see. When we run it with 1,000 trials, the speed up provided by the parallel approach, and all these numbers are in seconds. I probably could have printed this in a prettier way. But when we look at the speed up, this is not good. So the parallel approach takes 0.18 seconds. The serial approach is taking 0.0013 seconds. So the serial approach is faster, which means that the speedup is less than 1. If your speedup is ever less than 1, it's not good. It means your algorithm is not faster. And if it's close to 0, it means it's really not good because it's much slower. The question becomes, well, what should we do? And a natural thing to do would be to remember this value of 0.007 and multiply the number of trials by 10. Because if it's the case that we want parallel algorithms that have easy work that's obvious to split, point 1, but point 2, that when we split the work, each worker needs some amount of work to actually do to justify the overhead provided by the underlying parallelism that the language gives us, then this is only really going to work if they all get enough trials. So again, my computer has 10 cores. So let's give each worker 1,000 trials. And now we're going to see that the speed up has gotten quite a bit better. We went from 0.007 to, in this case, 0.09. It's still not worth it, but that actually was a big jump. So hopefully this continues. The idea here is if we chart the speed up, where the data is on the x-axis and the speed up is on the y-axis, we've started at a value of 0. It becomes worth it when we cross the value 1, and hopefully it continues past 1. That's as good of an argument as any as to why we care more about parallel programming these days than we ever had, because in so many contexts, the size of the data set grows. And as the size of the data set grows, there's more and more instances where a parallel algorithm is going to start beating the serial algorithm. So when we introduce 100,000 trials, the speedup goes up to 0.72. So we still have lost, but we've almost caught up. And when we go to 1,000,000 trials, we're going to see that we actually do obtain a speedup of nearly 3. Of course, the best I ever could possibly do is a speedup of 10 on this machine. But if I really cared about computing the house edge of craps, which I don't think it's a pressing scientific question of today because it's pretty well established. But if I had, an example Monte Carlo simulation like this, where it was clear that for the size of the data, it continues to get better, well, now I could take this and I could put it on a machine that has 1,000 cores. And if I got a speedup of 500x, it would really, really justify writing our code in parallel. And so that's really where we start to distinguish between parallel programming, which is kind of what we're doing here, and what I would call distributed programming, where we're running this on a machine with many, many cores. And that's where the real benefits of parallel programming start to arise. I could, of course, for this particular example, take it up to 5 million and then run again and see what happens. We see that the parallel simulation is done in 1.4 seconds. The serial one takes 6.7, and we get a speed up of 4.76. So as this number of trials continues to increase, we're really seeing the benefits of parallelization continue to grow. A simple idea, but a deep one, I think, at the same time, and something that would arise across a huge number of applications as like a foundational concept in parallel programming, that it's not worth doing it for small inputs, but for larger inputs, it is very much worth doing. And if I have a bunch of cores instead of just a small number of cores, it's also that much more worth doing, which is why parallel programming is so important, because we have a bunch of data, number one, and number two, we have many computers. All right. That's about all I want to say on the parallel crap simulator. I wanted to at least kick us off with a simulation that allows us to be a little bit more optimistic about parallel and distributed programming than maybe we were before when we just looked at summing the elements of a list. And so we can actually see a real example of a parallel algorithm that's faster, even on this 10-core machine, by making the jump from serial programming. Up next, we're going to do a diffusion simulation. So we're going to move towards a simulation of something a little bit more scientific. And in particular, it's going to be a simulation of a single particle diffusing with what we're going to implement this as a random walk. That's allowing us to take kind of the next step towards what we really want to do, which is to build a reaction simulator. So we're going to have points moving around, but they're also going to have the opportunity to interact with each other if they're close enough to each other. based off of a collection of rules that we have that are going to represent chemical reactions. And then we're going to see if we can, come up with some particular chemical reactions that allow us to witness, I think what you're going to see is some pretty cool emergent behavior from this. But we're going to need to start with just the diffusion of a single particle. If you have any questions, let me know. Otherwise, we're going to get started here on the second part. I should say, really, that's the same thing we did when we did Gray-Scott. So if you have done the Gray-Scott practice exercises, they follow the same model, which is the first thing we're going to do is implement diffusion, and then we're going to add reactions on top of that. So we're going to do the same thing with particles. All right. Let's get started then. To get started, we have some starter code in a diffusion folder. And we've got a collection of files here. I think it's fair to say at this point in the course, there are some things that I'm really just going to give you for free. What I want to do is I want to implement the engine, so to speak, in serially as well as in parallel of a single particle diffusing through space. We're going to represent that as a random walk, meaning that the particle is going to pick a direction of movement and then move in a single uniform length in that direction over a collection of steps. And we're going to do this for a lot of particles. So here's where the parallelization is going to come into play, because we're going to start with a bunch of particles, and each one is going to move along its own random walk. Eventually they're going to spread out, which we're going to see. And I'm going to allow us to have two different versions of the simulation. We're going to have one version of the simulation where we put all the particles in the center, and what you're going to see is they're going to spread out over time. And then we're going to have a scatter parameter here that allows us to just say, pick points along in two-dimensional space and place all of your particles somewhere randomly, uniformly within the box that we're going to use to represent this. Our usage here is going to say we're going to run this, and we're going to run it in serial, and we're going to run it in parallel also. And we're going to say how many particles do you want? How many steps are we going to run this for? How wide do you want the box to be when we draw in pixels, when we draw the visualization? Do you want them scattered, or do you want them all in the middle? And what's the drawing frequency that we have? So how many frames are there, or how many steps are there between consecutive frames when we make our simulation? I'm also just going to say, so all of our code is going to process our command line arguments, and it's going to, run our serial simulation, render it, run our parallel simulation, and render it. All of this is stuff that we've done quite a bit up to this point in the course. You're welcome to take a look at it. I am definitely not going to type it out concurrently. We even have a function called initialize particles that main is going to heavily rely on. That's just going to say, how many particles do you want? What's the width that we're thinking about in terms of the units here? What's the height of our box? So this is the size of the universe, so to speak. And what are the radius? What's the radius of each point? How fast are the particles moving? So how much do they jump in a single step? And then are they scattered, or are they centrally located? And then what we're going to get is a collection of particle objects. So this is not a very earth-shattering function here. It's just placing the particles in this two-dimensional space. We should say something very briefly about data types. So we're going to be using data classes, as we've often done with object-oriented programming. We have an ordered pair, which we've seen before. We have floats x and y that have default values of 0. The particle itself is going to have a position, which is our ordered pair. Remember, we need this equal field default factory equal ordered pair when we have user-defined classes as one of our attributes here. And then we're going to have a radius, which has a default value of 5, and a diffusion rate, which is the speed, so to speak, which has this default value of 1. So it's saying the default value is for it to take a step of unit length in each particular generation. So that's data types for us. Drawing.py is going to look very, very similar to how drawing often works. We take our frames that we care about, meaning we get a bunch of lists of particles. So each generation is its own list of particles, and so we have a list of all of those generations. We're also going to take a background color, what the particle color should be, and how frequently to draw these things, and then we're going to have a single draw frame that's going to, take these very similar parameters except for the number of generations, and produce a pygame.surface object associated with placing these particles on the surface. And then we've got an animate.py, and animate.py is going to have our old friend animate surfaces that takes this collection of pygame.surface objects that we have and where we want to write the video of this simulation to. And it uses this surface to numpy subroutine. So everything here is either identical or very similar to what we've already done. What I want to focus on is a serial implementation of this. Then we're going to have a parallel implementation of this. And sometimes we'll have helper functions that are just going to go into functions.py. We're going to start with a serial simulation here. I am going to move quickly through this because I think it's a relatively straightforward simulation to implement serially at this point in time. It's probably really, apart from the object-oriented stuff, it's going to be code that I think is relatively straightforward compared to what we've already done in the course, which is good. And this function simulate serial is going to take my list of particles. It's going to take the number of steps that I want to run this. This is the number of generations. And it's going to take the width and height of the box. So we're going to make sure that we know how big the box is. And the reason why is when a particle flies off one side of the box, it's going to wrap around to the other side. So as I track its position, I need to make sure that that's the case. If it's ever the case that, the x value becomes negative, well, I need to wrap it back around to the other side of the box. So the simulation here will be, the fancy word is that we're implementing it on a torus, which is like a donut, meaning you can go all the way around the donut and you wind up back where you started, or you can go around the central ring of the donut and you wind up back where you started. And so the idea here is the same. If you fly off the bottom, you're going to come back at the top. If you fly off the left or the right, you're going to wrap around. That actually will not be tremendously challenging to implement arithmetically, but we're going to start here with just our serial implementation of this particle simulator. So we will initialize a collection of time points. We start with this is our input list. So this is our initial collection of particles. And, let's create a lists of particles corresponding to the time points of our simulation. So when we do that, what we'll say is frames is a list of particles. Each of those lists corresponding to a single time point. And it starts off as empty, but what I really want to do is make a copy of my initial list of particles. So fortunately, we know in order to make that copy, I can call from the copy module, which we have imported. I can call deep copy, which will ensure that we go through all of our particles and make a copy of all of their attributes so that we have a fresh collection of data. Once I've done that, then I range over all the steps and update the universe. So I'll say for in range over, I don't want to start at 0, I want to start at 1 because I already have, the initial state of the universe is going to be where the list starts off. So I already have that in my list. So I'm going to go from 1 up to number of steps. And I want to include number of steps. So I'm going to go num steps plus 1. And then I want to say, well, let's look at our frames. Frames here is our collection of time points. And I want to append to that what happens if I say, update the particles of, and that's a function that I'm going to write here shortly, but update the particles of whatever the previous generation was. And as we're going to see, I need to give it the width and the height. That's going to be important because when things wrap around, I need to know how wide and tall the box is. So update particles will benefit from having each of those as inputs too. Okay. Then at the end of this process, I want to make sure, let's remember, we need to return that collection of time points. So this function probably should feel pretty familiar. This is the way that we've written simulations before, whether it was a cellular automaton or it was a gravity simulator. In each case, this notion of we're still doing something for a collection of generations. Of course, I need to write my update particles function. And so I'm going to put that into functions.py. And I have a function signature for it, along with the doc string that says, well, what's our current list of particles? What are the width and the height that I have? And what's the updated collection of list and particles corresponding to having a bunch of, each particle is going to be allowed to take one step in a random direction of the length associated with the diffusion rate. As we said, the particle positions are going to happen on a torus, so the updates are going to need to wrap around. And it's just a matter of writing this particular function. Now, in this case, I'm going to say the first thing I want to do is, if I'm going to produce a new list of particles, let's make sure I copy over the current list in a way that makes sure I get a completely fresh copy of my data. And so the first thing I want to do is have a line of code that says new equals copy dot deep copy of current. So that's my current list of particles. This is my new one. Once I make that copy, I'm going to say, let's range over all of the particles and update their positions. So to do that, I'm going to do a couple things. The first thing I'm going to do is to say for p in this new universe that I have, I'm going to call rand step of p, and everything in Python is passed by object reference. But if we have this instance of a user-defined class, it's going to be passed by reference. So I don't have to set p equal rand step of p or anything. I'm just going to call rand step of p. So this, this move in a random direction is what I would say here. But we also want to be careful. So it may be the case that we stepped off the side of the board. And if that's the case, we want to wrap around. And this is something that we've really kind of already seen, but the idea is we can do this by saying we're going to look at the x value, and it's equal to its current x value, but we're going to percent it by width. So that's a nice, clever little short example. It means if x gets too big, I'm going to divide it by the width of the box and take the remainder. So for example, if the width of the box was 10 and the position winds up being 11, well, when I percent that by 10, it's going to take me back to 1. So it's if I went 1 unit too far in the x direction, and I'm going to wrap back around. What's nice about this is that it also works in the opposite direction. So if I go to have an x value of -1 and the width is equal to 10, well, it's going to send me to 9. So that's where I want to be. And so I can tighten this just a little bit by saying I'm really just percent equaling by the width. I don't think we've seen that at any point ever in the course, but we're seeing it now. And we're going to percent equal the y coordinate of the position as well by the width. And once we've done both of these, now we ensure that the point is indeed still on the board as a result of the update. And all this function is doing is producing my new particle list where everybody got updated, moved in some random direction, and then we made sure that if we flew off the board, we tracked where it goes. And so I'm going to return new. So it might seem like a fancy idea, this idea that I'm implementing this on a toroidal surface, but at the end of the day, it's just these 2 lines of code. And they're the only places that this is going to actually even appear, because what I've done is I put them only here, and then I've passed all of the remaining work, which is to pick a random direction of motion and move this particle in that direction, to another subroutine called ran step. So all that function does is take a particle object, doesn't return anything, but it updates the position of that particle by moving it in a random direction, and its diffusion rate is going to tell you how far to move this. So if the diffusion rate is high, we're going to move the particle a lot. If the diffusion rate is low, then it's going to not move very far. So it's just a function of this diffusion rate. Captain Fuzzykins, you say that the Boyd's practice problem had wraparound. Yeah, but I don't think I had shown this on stream. So you're saying I should just assume that when you implemented Boyd's, you did it with 2 lines of code and no more. And you made sure you did % equal. I'll just assume that's yes. Ran step is just a little bit of dreaded math, though. So to write ran step, we need to think about how this function is going to work. Okay. The first thing we're going to do is move in a random direction. So the easy part here is to say, all right, I've got random imported. And so if I've got not angle is going to be pick a uniform random number between 0 and 2 pi. The angle needs to be in radians, and this is because when we work with angles in the math package, it's going to assume that we're working in radians. So we're going to pick a random direction of motion as an angle in radians. Once we have done that, we want to update the x and y positions, or coordinates, of the position of P. And we know that a particle has an attribute position. And so that's all we need to access is P dot position of something. But the issue, of course, here is, and where the math comes into play, is in functions.py. I've picked a direction of movement, and I know how far I'm going to move. We're going to move a length equal to the diffusion rate. Okay, so that's all right. And I think I've called this particle here. Okay, say particle dot diffusion rate. But then the question is, how do the x and y coordinates of the position of this point, how do they relate to this? And here's where our little trigonometry, I guess, comes in handy, where once I've established an angle of movement, the x coordinate corresponding to the change in x from my current x coordinate and where I'm moving. So if I go from here to here, for example, the x coordinate is just going to be cosine theta, and the y coordinate, or the change in y, is going to be sine theta. And that holds regardless of what the value of theta is. So theta could be down here, it could be over here. That's always going to be the case. And it's easy to generalize too, because, well, if this becomes an r, then this just becomes r cosine theta, and this is r sine theta. So I'm going to add the diffusion rate times cosine theta to the x coordinate, and I'm going to add the diffusion rate times sine theta to the y coordinate. And so again, I actually don't have very long code. I'm just going to say that particle.position.x is whatever it currently is, plus particle.diffusion rate times math.cosine of the angle. And I'm going to do the same thing for the sine. So I'll say particle.position.y is its current value plus the diffusion rate times math.sine of the angle. And that's it. So I don't need to return anything. The particle has been moved because it's passed by reference, and it's only really 3 lines of code. And that's it for our serial simulation. So we can, run this diffusion process for 10,000 particles if we want. In each case, we're just updating the system over a collection of generations, and in each generation, we're just letting each particle move in a random direction according to its diffusion rate. And then we're going to make sure to update its position in case it flies off the board, but otherwise we're done. That didn't take too long, which is why I wanted to just write the whole serial simulation and then have the idea here of how do I take this and convert it into a parallel simulation. So everything here is going to take, the same general, I'm going to have the same general plot of taking our particles, our number of steps that we're going to have. It's going to differ here a little bit because we're also going to have the number of workers, so numprocs. We're also going to have width and height to store the size of the board. And then we're going to say over a bunch of generations, each generation is going to give me a list of particles. And then I'm going to have a list of the generations. So on a high level, this is mimicking what we had before. It's just that we have a number of workers as an input too. So when we run when we write this simulation, the idea is how to take what we've learned and apply it here. So we're going to do the exact same idea that we had before, which is to say I've got a current universe, which is deep copy the input list of particles, declare a list that is a 2-dimensional list of particles to represent our time points. And I'm actually going to say current will store my current generation. And it will update as we go through this. So I'm actually going to deep copy the current generation at the starting point. And so now that I know that this is going to have the same values as what current starts off with, but it's going to be a different copy of my list. All right. Now, there's an important point to be made. And that important point to be made is to remember that we've got our, I think I called it a paradigm in my parallel crap simulator. I said, here's what we do. I'm just going to copy it over. Which is to remember, here's our collection of steps. We make a queue to store our results. We initialize our worker processes. We start all the processes. As they do their work, when they finish, they'll put their return values into the queue. We're going to range over all the processes again and join them, which just means wait until everybody is finished before you carry on. That brings us back to the land of serial programming once they're all finished. And we're going to grab all the results from the queue, and then we're going to combine them. So the idea here is, I'm going to make my point, which is it's very tempting to look at how we wrote our code before in the serial case and say, I understand what I do. I've copied my collection of input particles, and then I'm going to range over the number of steps, and I'm going to do this. So I could even copy this over. And in parallel, I need to make sure, way down here, I'm going to return frames. And in the meantime, I'm going to have a range over all of the steps that I do. And in each step, I'm going to say we want to do all of these. So we would make a queue. We would initialize our worker processes. We'd start the processes. We'd range over all of them and join them. And then we would grab all the results. This is not a great idea. Actually, that's a bit of an understatement. This is a bad idea for this particular example. The question is why, right? So, question for the chat. Why do we not want to do this? Before we even get there, maybe I've kind of made an assumption too, which is, how is it that this is going to get parallelized? The natural way would be to say every worker is responsible for like one equally sized stripe. So we're dividing out the area of our simulation. Everybody's going to get an equally sized piece of it. And if a particle flies into my region, I'm now responsible for it, right? So that's how this is going to work. But we have an issue here. So the question is, why is this structure going to be bad? Javier's got an example for us, which is lots of redundancy. Okay, which I think is on the right track. I like that. But what do we mean by redundancy? What would be redundant? Where is this redundancy living? I'll give you a hint. This computer has 10 cores. When I implemented craps in parallel, how many workers did I have? Javier says number of cores. Good. True. I had one queue and I had 10 workers. But then for this example, we have num steps queues. That's going to be a lot. But worse, way worse, is that we have num steps times num cores processes. And that's the extra frowny face, because we already see that processes mean overhead. Setting up all these processes means that things slow down. And it's okay if you set up a bunch of processes, as long as you have a bunch of cores, and each of those processes does a lot of work. But the problem here is you're going to create a whole lot more workers than there are cores on this machine. The number of steps that I want to run this simulation for is like 10,000. This computer has 10 cores, and now I'm going to have 100,000 processes. If you don't believe me, try implementing it in this way. You will see just how comical, and this is a combination of bad parallel design and Python being kind of infuriating sometimes, and this not being a natural language to do parallel programming in. But the combination of those two things produces a simulation that is so much slower than the serial one that it's like laugh out loud funny, or it was to me. That something that takes like 0.04 seconds on the serial world is taking like 34 seconds to run in parallel. So what it means is this is a lovely paradigm that I introduced. It was clearly important and valid when we worked with doing something like a Monte Carlo simulation where it's like, you each do your work and report back to me, perfect. But in this particular case, this is just an unbelievable amount of overhead. And so what we need to do is not do this. So our idea is, it would be a bad idea to create workers every time through a new generation. So the question is, what do we do instead? And, each worker is going to be responsible for a stripe of our space of equal size. And I'm going to say it's a vertical stripe. Okay. But the workers are only going to get initialized once at the very start. So we're not going to create number of workers times number of steps total processes. We're just going to create number of processes workers, and that's way better. So this computer is only going to have 10 workers. And the question is how to do that, because it's not something that we've seen thus far. And what we're doing is create a pool. So the function that I want to call from multiprocessing is called multiprocessing.Pool. And how many workers do I want to create? Well, it's numprocs. This is a pool object. We're not going to go deep into the pool. But what we are going to do is say, well, we've got a pool object. I'm going to call it something. I'm going to call it pool. So this is just a collection of workers. And the pool is going to allow me to have workers that persist for a collection of different things that they're going to do. In the Monte Carlo simulation, they were all doing a lot of work, but they're only getting one task, which is go simulate this 1,000 times and come back and report back. In this particular case, every step, we have to give them an updated set of instructions. It's like if they're playing a game, but what we tell them to do changes every single time that they play. In that particular case, I would need a pool instead of go play 1,000,000 times and come back when you're finished. And so here's where the pool gets really useful. You could have your pool be, I don't know, half the number of workers, and then, half of your workers are going to get left out, or it could be times 2, in which case I believe what's going to happen is everybody's going to get 2. The natural way of doing this is to say, create a number of workers equal to the number of processors that you want. And so once we've done that, we want to range over all the steps that we want to perform. Now it's okay to do it, to say for as we range over 1 to num steps plus 1. And once we do that, we're going to say, all right, divide the space. So I'm going to have a variable called stripes, and I'm going to call a subroutine called assign stripes that takes the current generation, the current universe of particles. It takes the number of workers that I'm going to have, and it's going to take the width as well. And the reason why it's going to take the width is I need to know how wide my space is so that when I chop it up into stripes, everything is going to work out, right? So if I have 10 workers and my width is 100, well, I want each stripe to have width 10. And this is going to allow me to know, which sector of the space is each worker assigned to. So in functions, I think is where I've got assigned stripes here. What we're really doing is saying, so I should say, stripes of 0 holds the particles associated with worker 1 or worker 0. Stripes of 1 holds particles for worker 1, and so forth. In general, stripes of I holds the particles associated with worker I. So there needs to be a subroutine that says, here's my particles, here's my workers, which particles get sent to which worker. And that's what this assign stripes function is going to do. if I assume that that subroutine has been written, all right, what I want to do is say, next, assign each worker precisely one stripe. Okay, so I'm going to say, for all of your stripes, I'm going to say worker args, and I need to declare my worker args. And so before I do that, before I even do this, let me do something else. I'm going to say moved stripes is equal to, I'm going to access the pool, and I'm going to call a very fancy function. I think parallel programming is pretty straightforward at the end of the day. A lot of the examples that we're going to see, you know, we followed that same set of 5 steps. In this case, we're going to call a function called starmap that is associated with this multiprocessing.Pool object. So I've got my workers, they've been made, and this pool of workers is going to have this function called, or this method I should say, starmap, that's getting called. And what starmap needs to know is a couple of things. So it needs to know what function do you want to call, and the function I want to call is update particles. You will see I've already imported that at the top from functions. That is a function that we've already actually written, right? So when we look at functions, we have written update particles. It is a serial function. Again, the beauty of if we have a coherent parallel design, the idea is it will use serial functions here and there. And this is an example. If I divide this over a bunch of workers and say, you as worker I get this particular choice. I just noticed this needed to be height. You as worker I get this particular choice collection of particles. To update those particles, what am I going to do? Range over all the particles and move them all. So they're all going to take a random step. So there's nothing parallel about that. What I want to say is, all right, well, when I call pool.starmap, it's going to, the first argument is the function that I want to call. And so this function is going to get called on every single element in the pool. So each worker is going to get update particles. But what we need to give it is update particles of what? And here is where we actually have multiple arguments that need to go into update particles. You can see that because you give it the current list of particles, and you also need to give it the width and the height of the space. And this is the overall space that it's getting access to, not just its stripe, because if it flies off, we need to wrap it around. And so because you have 3 of these parameters, what you need to do is to give it those parameters as your second argument. And so this is what I'm going to call worker args. And worker args is going to be, I think, a tuple of those 3 things. It's going to have the 3 things that update particles want. It's going to have the list of particles that need to get updated, and it needs to have the width and the height. So the worker args has not been defined. And what I will do is I'll say exactly what that is. I'm going to declare it. Okay. And the worker args in this case is just a list. So the length of the list is going to be the number of workers. Okay. So it's going to be the size of the pool. And so that's where I'm getting the list from. This list is going to start off as empty. And each element needs to be 3 things. Each element is the parameters that I'm passing in to update particles. And as I've said a couple times, that choice of parameters is my list of particles, the width is a float, and the height is a float. Which means that what I want to give it is each worker is getting a tuple of 3 things. A tuple of a list of particles. That's argument 1. The float corresponding to the width, and the float corresponding to the height. This is about as good of an example as I could ever come up with as to why even though this is not required that you do this type of thing in Python and give yourself type hints and understand, code that looks like this, I just can't imagine typing this out as this. Like, that helps who? Right? Like, even an AI bot would be like, nothing wrong with this. Like, understanding what exactly my three things are going to be. Okay, rant over. Of course, this is an empty list. So what do I want to do? Let's assign each worker, or I should say, the ith worker, the three parameters that update particles needs. Okay, so I will say for each stripe in my stripes, this is a list of lists of particles where the ith stripe holds the particles that the ith worker cares about. So we're going to range over all those stripes. And then I want to say, all right, go into worker args and append to it three things. The stripe. That's the collection of particles associated with worker I. Great. And then width and height to tell me how big the box is. And we're using a star map. I think a lot of times when you do this, you declare your pool. And you would just have pool.map. If you have seen that before, the reason why we have to use a star map is because the function that we're calling for each worker, update particles, is getting more than one parameter. So what worker args is doing is making sure that we're communicating all of the parameters that are getting passed in for the ith worker. Now, once I've done that, remember, I'm appending a tuple, so I want to be very careful here and make sure I do it that way. Once I've done that, I have the parameters that are associated with the current worker. What this is doing is starting, so this starts the process of each worker calling update particles on its stripe, meaning its subset of particles that it was assigned. And as the particles spread out, hopefully everybody's going to be about equal, but we no longer have the control of that. So if all the particles are in the center, for example, a stripe that's on the outside is not actually going to get assigned any particles. So that's something to keep in mind. This is another kind of example in which this particular simulation can be a little trickier than what we've seen before. But the idea is, at the end of the day, every worker is getting some collection of particles assigned to it. And pool.starmap is going to start the process of them doing their work. Okay. And the critical idea here is the star map blocks until they are all done. And that's a good thing. Okay. We want them all to be finished. They're all working in parallel when I call this, but I don't want to come back here and ask them how they did until I make sure that they're all finished. So in other words, we wait on them to all finish. You can only, I guess, be as fast as your slowest worker in this particular case, which is something we've seen before. Once they're all finished, let's combine their work. So I am going to create a new value for current. In this particular case, I'm going to violate my principle and just say, it's an empty list. And what they have ultimately done is updated stripes by saying, if you look at what update particles does, each worker is going to return a list of particles. So all of this, what's nice about it is we don't have to manage the queue anymore. All of this is just kind of working behind the scenes. And at the end of the day, each worker is going to produce a list of particles. And that collection of lists of particles is what we call moved stripes. Okay, so at this point in time, moved stripes is a list of particles where moved stripes of I has particles associated with moved particles. It should say it has the particles that were moved by worker I. And that's nice, because if I've got that, I can just say, oh, we'll just take the current stripe and range over the moved stripes. Okay, so at this point in time, stripe is a list of particles. And if that's the case, then all I have to do is take current and append that list to it. So what current is a list of particles. It starts off as empty. One little thing is that this is not how append works in Python. You need extend, which does the same thing. So if I have a list and I want to add, another list to the end of it, I call current.extend. Once I've done that, at this point in time, we now have updated positions of all particles, and I will add the current snapshot into frames. So down here we're going to return frames, but for now I'm going to set frames.append, and let's make a copy of that current time stamp that we have. Once I have done all of this, so I'm outside of the engine that I have, this is doing this for a collection of steps. Once I've done it, then it's just a matter of outside of the loop indicating I know that I'm finished. So at this point, we're going to indicate that work is done and the workers can be, let's say, retired. All right, let's be nice to them. And we do that with two functions. We say pool.close says no more work is coming, and pool.join says you're all fired. And thank you for your service. All right. And I think there's certain contexts where this would wait for them all to finish, but we know that they're all finished at this point. And then we can return the frames. And that's our function there. That's the engine of our parallelism here. There's only one other thing to do because I already have written update particles. What I have not written is the little helper function that says, take my current universe of particles, take the number of workers that I'm going to have, and take my width of my box and divide out my space into stripes and figure out, which worker gets which particles. So stripes of I is going to hold the particles associated with the ith worker. And so that function works by taking my list of particles, my number of stripes. I like calling that number of stripes here instead of just number of processes. We've indicated that's probably equal to the number of processes, but it's a more general function. And then this is the width of the space. And this function is quite a bit more straightforward because what we're going to say is, how wide is the current stripe? That current stripe just needs to be, we're going to call this stripe width, and that's the width of the universe divided by the number of stripes. Then we're going to make my list of stripes. What is stripes? It is a list of things. Remember I said stripes of I is the particles associated with worker I. So I will say stripes of I holds the particles associated with worker I, which is a list of particles, and we have a bunch of these things. So we're going to have a list of particles. It's going to start off as being equal to the empty list. And then it's just a matter of, range over. Actually, first thing I'm going to do is let's range over the number of stripes. And I'm going to say everybody starts off as an empty list. So every worker starts off receiving an empty list of particles. And then we can say range over every particle in the universe. And when I do that ranging, assign the current particle to the worker that it should be assigned to, okay, based off of where it falls, like which stripe does it fall into. And this isn't too bad. So we say, let's range over the particles. And then what I'm interested in is, what is the X position of the particle? The Y position is irrelevant to what stripe I'm in. It's all a function of where I fall, in terms of the X-axis. And what I want to do with that X value is divide it by the stripe width. And both of these are floats. So this is a float. It's tempting to say, well, I just want an integer division like that. But because they're both floats, we need to, I think, do it as divide them and then take the integer of the result. Okay, so in other words, imagine that the space has width 200 and we have 10 processes. So we have 10 stripes. That means every stripe. So for example, we have 10 processes and width is equal to 200. Now, if, the X coordinate of the particle's position is, 47, right? Then how would we figure out which stripe it goes into? You could divide 47 by the stripe width. So the stripe width here is equal to the width divided by the number of stripes, which is going to be 200 divided by 10, which is equal to 20. And now we see how we're going to get this, because we'd say, well, if you're at X coordinate 47, you belong in the third stripe. Why? Because if you're between 0 and 20, you go to stripe 1. 20 to 40, you're going to go to stripe 2. And 40 to 60, you're going to go to stripe 3, and so on. So 47 divided by 20, when we take the integer, what's nice about that is it's going to round down. The integer of this is the integer of 2 point something. And when we do that, we're just going to get 2. So when I perform this integer of p dot position dot x divided by stripe width, it's going to tell me the I that I care about. A lot of times you'll see this as like index, but really it's just I. So that's the assignment. I is the index of the worker that this particle should be assigned to. And I can do that just by saying stripes of I dot append the current particle to it. So that does the assignment. And then at the very end of this process, of course, we're going to return our stripes. So a little bit of dreaded algebra here with something that is actually much simpler than it might seem. And again, as is often the case, amazingly, presto, we're finished with our simulation because we only actually have 2 functions here. And the subroutine that the workers are going to call is update particles, as we have said, which we've already written in functions.py. So we should be able to run this now. The question is, do you believe that it's going to work? Are we going to get a speed up? Is it going to be greater than 1 or less than 1? Only one way to find out. So that's what this is going to do. It's also going to make, we've got animate.py and drawing.py. All that's just going to allow us to visualize what we're doing. So we're going to see the simulations too. Okay. Are we getting a speed up? That's my question. So our usage here, I got it somewhere. Number of particles, number of steps, how wide is the universe? Are we scattering them, or are we plonking everybody in the center? And then how frequently are we going to draw? So I can run, I'm not in the right folder. So I'm going to cd into src diffusion. And then I'm going to run Python 3 main.py. And now I need to know, let's establish some simple values here. 500 is the number of particles. Let's run it for 100 steps. Let's do a width of 200. Let's center them. Everybody's going to start in the center. And the drawing frequency is going to be 10. So every 10 steps, we're going to produce a frame of our animation. I've still got my poll. Do you think we're going to see a speed up? In other words, is the ratio going to be bigger than 1? This is like a US election. We have 2 votes. Everybody's abstaining. They want a third candidate. All right. Or you're just confused and not sure. Or you think I'm probably trying to trick you. Okay. Let's see. Module math has no attribute pi. Did I mean pi? Probably. Where was that? In the functions. Okay, let's try it again. All right. So the answer is never, it's never good, right? Our serial simulation took 0.249 seconds. Parallel took 1.093. So our speed up is 0.23x, which is not bigger than 1, and that's not good. Now the question is, well, what should we do? And from our Monte Carlo simulation of craps, I think it's clear that what we need to do is increase the size of our data. But with implementing this Monte Carlo simulation of craps, we only had one parameter. It was the number of trials that were running. So as that went up, our speed up improved. Great. But the issue here is that we've got a lot of different parameters, right? So if you look at main, we've got the number of particles. We've got the number of steps that we run this for. We also have the width of the universe, which, I don't know how important that'll be. We have scatter and center, which is another parameter. And then we have the drawing frequency. This relates only to drawing, so we're not going to be interested in it. This could perhaps be important, but which of these, my question to you is, which of these parameters do you feel like is going to affect the speed up the most? Like, which would you be the most hopeful about, that if we increase it, hopefully we would see a positive, or not a positive, but a speed up that's greater than 1. Which, if you had a choice of one of these parameters, which one would you choose? Or it has an immediate vote of number of particles. Why would we think that? Why number of particles? So there are two things that matter, right? If we're going to see a speed up, we have to have two things happen. Thing number one is we need to make sure that this is a problem that we can easily divide up into pieces. And we had to deal with the worker pool. But at the end of the day, actually, once I set that up, it wasn't too bad to just divide the space into stripes and say, you go to this worker and you go to this worker based off of where you landed in the space. So that's definitely there. But then remember, there's part two. And part two is that, well, each worker has to be able to do enough sophisticated work in order to justify its creation. So it's going to take some time to set up all of these worker processes. And if that's the case, we need to make sure that we're giving them enough to do. If I have 10 cores, what have I run this on? I've run it on 500 particles. That means on average, each worker is only getting 50 particles that it's responsible for. That's not very much. And so we could try to change like the other parameters that we see. So I could change, let's keep everything fixed, but let's run our simulation for a larger number of steps. So I still have 500 particles, but I'm running it for 10 times the number of steps. That actually helped a little bit. So our speed up went from, I think, 0.23x to 0.36x. So it's not that it's irrelevant. And when we look at our output, I've got my particles a little bit big here. And it's because I'm not making a very pretty simulation. But the idea here is that's okay. I think the width of my space is not very big, and that's just because I wanted to make a fast simulation. I could fix that if I go back, and I want to run it for 100 steps, but I ran it for a width of 2,000. And we're back at the speed up of 0.25, and now I probably made it too small. Yeah, I haven't actually run this for many generations at all. But if I go back to 1,000 and then have this width of 2,000, we're rendering the serial animation. We can take a look at it. We know that the parallel animation is going to be, or simulation is going to be slower. But here is our simulation of the particles, which on its own is pretty, right? We can run a longer version of that. In the meantime, we're running this parallel animation. We saw for, I think this was 1,000 steps. We're able to see a speed up that's a little bit higher. While I'm doing this, I may as well also scatter them and see if that changes anything. So we're going to scatter all the particles that we see. The serial simulation is finished in about the same amount of time, which is what we probably should expect. Parallel is going to run. We'll see if we see any improvement with parallel. In the meantime, I'll show you serial. There's like little stars there. And we can run this for a lot longer to see this, but yeah, that seems to help a little bit. AKB, thank you. Good job. Scatter seems to help. And that makes a lot of sense because if everybody's clustered in the center, I have a lot of workers that are just kind of sitting on the sidelines, waiting on a particle to make it to them because we gridded off the space, but they didn't actually get assigned anyone. So scatter should, in theory, help. So that's another parameter that when we change it, should help with our speed up. So we've seen number of steps actually helps. Scatter also helps too. What we really should do is I'm going to lower because I'm not interested so much in the animation prettiness, and I'm not interested so much in the number of steps. But what happens if I raise the number of particles to like 5,000? And I'm going to keep scatter. Our hypothesis was number of particles is probably the most important parameter here with respect to trying to get us a faster simulation. And they scattered, so they kind of, I think there were a lot of them here. Yeah, so that's our issue. You look at this and think, is it broken? But what we did was we've put so many particles, we put 5,000 particles on our grid that when we scatter them, they're all just overlapping with each other. So these these little black specks are the only places that actually don't have a particle over them. And so when you scatter them, you eventually just lose it. So the simulation's, the animation is hideous, but we're running this because we can make it prettier. I don't think this is going to take too much longer. Let's see. Yeah, so there's our serial simulation. And it's not running for many steps because I wanted to run this on a lot of particles. And you can see that. But our speedup is still only 0.42. So, maybe we could take this to like 10,000. I don't want to run something that takes too long to finish. But I think this is probably going to take about twice as long. Probably should scale like that. Yeah, the serial simulation is finished in 7.44 seconds. We can still see them there. And our parallel simulation is still only 0.39x. So the good news is we didn't do this using the same approach that we did before with parallel craps, where every step of the way we initialized a bunch of workers. In that case, the speedup is going to be 0.000 something, and the parallel approach is not going to be very good. It is true that the main argument that we want to change here is the number of particles. But there's other issues here. Issue number one is there's stuff going on behind the scenes where Python simply just has more overhead associated with it than other languages. So you have to go farther out in terms of the size of your data in order to finally see an improvement. Part of that's just the language and the fact that it wasn't designed to be a parallel programming language, even though it has support for it, which is great. The greater issue here is that the workers just don't have enough to do. At the end of the day, and we just need to probably run this for a larger number of steps and a larger number of particles, because at the end of the day, all that these workers are doing are getting their, I'm getting my stripe, and I'm updating the positions of the points, which is good, but I'm only updating them 100 steps, right? So I need both of these parameters to be increased. What I really would love to see is something like this. And that's going to take a period of minutes for this particular implementation to complete. But I need both a lot of particles and I need a lot of steps for it to be worth it for me to go through the process of dividing all these tasks off to all the workers and make sure that all these worker processes actually have enough to do. So that's that second really important part of it, which is that we've parallelized the algorithm. It makes sense, but all the workers have to have enough to do to justify their creation. And that's not quite the case here because what they're doing is so simple. They're just going through and saying, oh, I found a point, just push it a little bit. And one of the things we might do is not constantly reallocate all of the particles to all these different workers. That's one way that would really kind of speed this up a lot. And in that particular case, then each worker just knows which particles it's updating, and every so often it gets assigned a new collection of particles. That's a really nice idea. I would do that if the purpose of this was to try to get my speed up to go over 1. And that would get us there. I'm not interested in that direction, not because it's not good, but because I want to do something else. I want to give the workers a lot more work to do by also adding chemical reactions to this simulation. So I want it to be the case, which if you did, for example, our Gray-Scott exercises and got the practice there, it's not going to be a surprise that we want to have reactions like, I've got 2 different types of particles. I'm going to have a predator and a prey. And if a predator encounters a prey, maybe the predator eats the prey. Or I'm going to have 3 types of particles, and they're going to be like rock, paper, scissors. X is going to eat Y and form a new X, and Y is going to eat Z, but Z is going to eat X. And so how is it that if I add these sorts of interactions to this, well, now I've got a much harder problem because each worker is going to need to look at its particles and say, okay, which particles of the appropriate configurations are close enough to each other to maybe interact with each other according to the set of rules that I have. And then I want to apply those rules and see how that changes the simulation over time. Now, all of a sudden, each worker is going to have a lot to do. They're not just pushing particles around in little directions. They need to go through and measure what are the points that are nearby each point. If I do that serially, this problem becomes very challenging because, well, I can implement a fancy data structure or something like this, but I would need to find some way of saying, well, how is it I would organize and know that this collection of particles are near each other? That's a lot of work. And if I grid off the space first, it's going to greatly reduce the amount of work that I have, because in one particular stripe, I'm only going to look at the points that are near me in my stripe. And that's going to speed this up greatly. So that is the hope that I'm going to present to you, that parallel programming is not hopeless. It's just often a little bit clunkier in Python, and we need to make sure that once we've divided the tasks, all the workers make sure that they have enough labor to justify their existence and to justify this overhead of splitting the tasks up. That is it for now. I'm going to let my simulation run. I would actually say, see if you can beat me. So post your own simulation to our Discord if you can get a working example of a speed up that's greater than 1. I'd love to see it. Otherwise, that's going to be it for now. And next time, we're going to make sure that all of our workers get more labor in the form of a lot of chemical reactions that we're going to add to our simulation. And we're going to run this for a lot of different types of chemical reactions. And we're going to see some really pretty visualizations and actually be able to make some pretty cool high-level conclusions around certain systems of reactions that we're going to study. But that's plenty for now. And I will plan on seeing you next time. And as always, until then.